So now I just want to continue our discussion about vectors. So just where we left off in the last video with this form right here, let's kind of write this out formally now. This is called component form. So this is where we write the vector as if it has initial point 0, 0, oops, and terminal point x, y. Okay. So then the vector would look like v is equal to x, comma, y. So we find the equivalent vector with initial point 0, 0 and terminal point x, y, and we can just simply do that again just by subtracting the coordinates. So like in this case, we just subtract, and we do 8 minus 1, terminal point minus initial point, etc. So we find this by doing terminal point minus initial point. Okay. Okay, so let's look at now, how do we, this is called component form because, sorry, these right here, these are called the components of the vector. Okay. All right, so now let's look at how do we actually calculate that magnitude. Okay, so we can see how it's represented by the length of the vector, but how do we distill that into a number? How do we actually find the magnitude of a vector measured as a number? So if a vector is in component form, so we'd say v is equal to x, comma, y, then its magnitude is given by, we write it with a double line, so v like this. So we have double lines on it, so it's like the absolute value except for we have two lines, and that's not an accident, is equal to the square root of x squared plus y squared. Okay. So you might recognize this as the distance formula, which might not be too surprising if you think about what's going on in the plane. We're basically just finding, if I scroll back up here, if we need to find the length of this line, well, then we're finding the distance between the initial and the terminal point, right? And so first, if we find the equivalent vector where the initial point is 0, 0, the terminal point is x, y, then the magnitude of the vector is given by, this would be x minus 0 squared plus y minus 0 squared. So it's just the distance formula, which the distance formula is just the Pythagorean theorem. Okay. So this is not an accident that it's very similar to the absolute value notation. The lines are usually kind of closer together. So let me show what that would look like. Because if you distill this down into one dimension, then that is the absolute value, right? The absolute value of x is given by the square root of x squared. So they are very similar things, and they follow similar rules. For example, the magnitude of a vector is always greater than 0, right? This is always going to be positive right here. It follows a handful of other rules, like for example, it follows what we call the triangle inequality. which is that if you have two vectors, v and w, their magnitude is less than or equal to the individual magnitudes. Okay, this holds true for absolute value as well. We haven't really, we didn't really use that in the other classes or anything. This is a very useful thing when you're proving things, to kind of break up an inequality into two separate inequalities. But yeah, it just hasn't really come up yet. So yeah. So let's go ahead and find the magnitude of some vectors. Okay. So for example, if we look at the one we just had, 7, 4. Okay. So let's say this is equal to v. Then the magnitude of v, or maybe you just, if you don't give it a name, maybe you just write it like this. That's fine too. So this would be equal to the square root of 7 squared plus 4 squared. So the square root of 49 plus 16. So the square root of 65. In general, you don't really need to simplify the square roots. It might come in handy sometimes. I don't think this one really can be simplified at all. That would just be 13 times 5. So yeah, there's nothing we can pull out of that one. So if we look at the vectors 1, 1, for example, that was another vector we looked at. Its magnitude would just be the square root of 1 squared plus 1 squared, so it would be the square root of 2. Okay. Now, if we looked at the magnitude of negative 1, negative 1, this would also be the square root of 2, right? Because the squareds take care of those negatives. So, again, this makes sense graphically. If we think about this vector being the vector 1, 1, and then we think about this vector being the vector negative 1, 1, or negative 1, negative 1, we can see that they have the same length. So it makes sense. It's the direction which is different between the two.